Okay, here we are on section 5.1, and we are going to do the warm-up. So they have a number of observations listed, and then they want to know whether these observations are things for an acid or a base. So you tell me, what turns phenolphthalein pink? Base, good job. Yeah, phenolphthalein turns somewhere around like 8.2-ish pH, which is slightly basic. Feels slippery. Bases, yes. They feel like you've got like some soap on your fingers. What has a pH of 5? Acid, yeah, because pH is less than 7 are acidic, greater than 7 are basic. What tastes sour? Acid, yeah. What conducts electricity? Both. Yeah, good job, because both an acid and a base will produce some freely moving ions in solution. Whether it produces a ton or just a few is determined whether it's a strong or a weak acid or base. What reacts with metal to produce a gas? Acid, exactly. Okay. We're going to be covering 2 different definitions for acids and bases today. We'll probably only make it through the first definition before break. The first definition is known as the Arrhenius definition for acids and bases. It was developed by a chemist by the name of Savant Arrhenius. And according to Arrhenius's theory, he said that acids will release hydrogen ions into solution, and bases will release hydroxide ions. Okay. Now, you know that when an acid combines with a base during a chemical reaction, you're going to produce a salt and water. This is known as a neutralization reaction. It releases a little bit of heat. Neutralization reactions are special types of double replacement reactions. Okay, so these are exothermic. And you know that acids will contain a hydrogen ion. Generally speaking, bases will contain a hydroxide ion. Salts are also ionic compounds. Remember, ionic compounds contain a metal or the ammonium ion, and then water is either written as H2O or HOH, doesn't matter, okay? Now, let's take a look at a sample problem. So here they want us to classify each of the following substances as being an Arrhenius acid, Arrhenius base, a salt, or a molecular compound. So if you take a look at the first one, HNO3, what would this be? Acid, because it contains a hydrogen ion. How about B? Base, because it contains a hydroxide. C? Salt, because salts are ionic compounds, and ionic compounds contain a metal or the ammonium ion. Aluminum is a metal. And then NO2 would be? Molecular, because nitrogen and oxygen are nonmetals, and that's what molecular compounds are made of. Okay, let's take a look at the next page. On the next page, they ask us to classify these substances as well. So A is H2SO4. What would that be? Acid, because it contains a hydrogen. How about XeF6? Molecular, because those are nonmetals. How about C? Careful here. Yeah, this is an acid because, do you remember on your periodic table how you wrote this ion over the acetate ion, which is C2H3O2 -1? Okay, so this is the acetate ion, which is attached to a hydrogen. You're used to seeing this acid written like this. Okay. Your book tends to write it as CH3COOH. The real reason why they do that is because this is CH3COOH. Okay, so this all goes together structurally, and then here's that hydrogen ion attached to it. Does that make any sense? Okay, how about D? Yeah, this is a salt, which is an ionic compound because ionic compounds contain a metal or the ammonium ion, and sodium is a metal. How about E?
Base.
Yeah, because it contains a hydroxide. And then F. According to the Arrhenius definition of acids and bases, NH3 would be a molecular compound. Now, this is actually a weak base. Okay? That's why I'm going to have to introduce a second definition for acids and bases, which is sort of broader. And I'll do that after we do number 2. Okay? Yeah.
Going back to acetic acid, how do you know if it's a full hydroxide again, or just a weak one that is out?
So bases are going to be a metal with the hydroxide attached. Okay? Does that help?
So it can only be next to a metal.
Yes. Yes. If you have a hydroxyl group, which is a hydroxide, sort of like a misnomer, but if you have an OH in a group and it's on the end of a molecular compound, that's when you have to ask yourself, okay, like, remember how we had that alcohol earlier in like a previous chapter, like ethanol? Okay, so when it looks something like this, they would refer to this not as a hydroxide, but more as a hydroxyl group because it's in a molecular compound. Does that make any sense? Okay, and it wouldn't leave as an ion. Okay, it would stay intact as a molecule. Okay, let's take a look at number 2. They want us to complete these neutralization reactions and predict the salt produced. So what I want to do is let's take a look at C, and then we'll go on to number 3, and then we'll probably be ready for break. So remember, these are special types of double replacement reactions. Therefore, I would write them out in words first, then convert the words to the chemical formulas. So here we have magnesium hydroxide. And instead of writing this as phosphoric acid, which makes it difficult for you to predict what products will form, write acids improperly. Write it as hydrogen attached to some ions. So this is hydrogen phosphate. Okay. Then the cation, or the first substance that is in each chemical formula, those will switch. So the magnesium and the hydrogen will switch places. You will end up producing magnesium phosphate. And hydrogen hydroxide. The order that you write the products doesn't matter. You could write hydrogen hydroxide first, magnesium phosphate second. But what does matter is that the cation is listed first. So you will always have the cation followed by the anion in the chemical name or the chemical formula. Okay? So over here we've got magnesium phosphate, which is this. So this is going to end up being Mg3PO4 And then hydrogen hydroxide is just HOH or H2O, whichever you prefer. I'm going to write it as HOH. And then for balancing purposes, I've got 3 magnesiums here, so put a 3 here to balance the magnesium. Then you've got 3 times 2, so you have 6 hydroxides. So put a 6 over here to balance this hydroxide. Then you've got 6 hydrogen, so you would need to put a 2 here. 2 times 3 is 6. You've got 2 phosphates on either side, so it's 3, 2, 1, 6. They're asking you to identify the salt, right? This would be the salt. It's always going to be on the product side, and the salt contains a metal or the ammonium ion, and magnesium is a metal. That's how you know, okay? Okay. Lastly, number 3. Number 3 gives you a bunch of salts. So what I'm going to do here is I'm going to write that these are salts. And then they ask you from that salt to identify what acid it came from. They call that the parent acid. And what base or parent base produced it. The way that you want to do this is you want to take a hydrogen ion and combine it with the anion that is in the salt. And then for the parent base, you're going to take the cation that's in the salt and combine it with a hydroxide. So over here, if I break down, I'm going to do this in a different color. If I break down my salt into its ions, this is going to form a potassium ion and a nitrite ion. This is the ammonium ion and a chloride. This is, I believe, copper 2. And then on your periodic table, does it say on the bottom left, C2O4 negative 2? Is that oxalate? Yeah, okay. And then I just use it really infrequently. And then down here, this is the sodium ion, and then we've got the acetate ion. Okay, so from here, my parent acid for A would be hydrogen with this anion. So this would end up being HNO2. That's my parent acid. The parent base would be this cation with hydroxide. So it would be KOH. Okay. Then for B, hydrogen with chloride would be HCl. For the base, it would be this cation with hydroxide. So this would be NH4OH. For C, you're going to put hydrogen with this oxalate. So this would be H2C2O4. And then put this copper 2 ion with hydroxide. So this is Cu parentheses OH parentheses 2. And then this last one, put hydrogen with this acetate. It's deemed improper to put the hydrogen in front of the acetate ion when it's written like this because its structure can't accommodate hydrogen next to the carbon, if that makes sense. So that's why the hydrogen is always put on the end. And then take your sodium ion and combine it with hydroxide. So this is NaOH. Okay. And then I'll introduce Bronsted-Lowry, but we're not going to get into it before we take our break. So can I move the board up? This is good. Okay. Let's leave the Arrhenius definition of acids and bases because it's pretty limiting. And let's talk about Bronsted-Lowry for a second. So you saw how NH3, according to Arrhenius, is a molecular compound, but NH3 actually feels slippery like a base, and its pH is greater than 7. It turns phenolphthalein pink. So we need a broader definition, which incorporates this Bronsted-Lowry definition for acids and bases. According to Bronsted-Lowry, acids will give up a hydrogen ion to something else. Since hydrogen ions have a positive charge, you will notice that they also call them protons moving forward. And then bases will actually accept a hydrogen ion from something else. So to give you an example, let's take a look down here in this reaction. You read these reactions left to right typically unless I tell you to read them in the reverse direction. But here I'm going to partner up HCl with Cl negative 1 on the right-hand side. And as you read it from left to right, do you see how we had a hydrogen here, but I don't have a hydrogen on the right-hand side anymore? So that means we went ahead and we donated a hydrogen to something else. So that's why they put acid underneath HCl, okay? Then when I partner up the H2O with the H3O plus on the right-hand side, you're going to notice that we went from H2 to H3. So that means we were accepting a hydrogen from something else. And according to Bronsted-Lowry, that makes H2O a base. Typically, we only write acid and base on the reactant side, and then we label the products something else.